Hello everyone, my name is Arman, and today I will be presenting a session called Terraforming Earth, how Terraform bridges the multi-cloud gap for the Earth observation community. And this is me, my name is Arman Karatosun, and I am Cloud Data Access Services Expert at UMESAT. You can of course reach me from my social media. Before going any further, I will start by introducing you to the European public space sector. But I must say that I do not hold any official position to represent any of the institutions that I mentioned below, and the information that I'm sharing is just the online available information. With this in mind, let me introduce you to the ESA, or European Space Agency. Well, it is Europe's gateway to space. ESA works together with the national agencies, institutions, and organizations and has 22 member states. ESA coordinates several missions and programs, most notably Copernicus program and Galileo, in close coordination with other agencies. EUMETSAT stands for the European Organization for Exploitation of Meteorological Satellites, and it operates satellites for monitoring weather, climate, and the environment. EUMETSAT works together with national agencies as well, institutions and organizations, and it has 30 member states. EUMETSAT operates several series of satellites, including Meteosat and Sentinel series, and it also has a data archive and online data lake, which contains more than 10 petabytes of data, spanning more than 300 products. I also would like to highlight that I worked at EUMETSAT as cloud computing engineer between 2019 and 2022, and now as Cloud Data Access Services expert since July 2024. ECMWF stands for the European Centre for Medium Range Weather Forecasts, and it provides 24/7 operational service, producing and disseminating numerical weather predictions to its member and cooperating states. ECMWF hosts high-performance computing facility as its core of its operations, as well as meteorological archival and retrieval system called MARS, which provides access to meteorological data that has been collected or generated at ECMWF for almost 40 years. In addition to that, ECMWF also hosts a cloud infrastructure in close coordination with HPC-related activities. I also would like to highlight that I worked at ECMWF as cloud computing engineer between 2022 and 2024. Of course, these institutions work hand-to-hand with other institutions such as European Commission and European Union and partners from the private sector. Well, let's talk about Earth observation data and its history. Let me tell you, it's a bit complicated. It all started with FTP server in the beginning, or an NFS share or threads data server, but everything has changed when the Cloud Nation attacked. Since the launch and success of the Copernicus program in 2014, the amount and the size and the quality of the Earth observation data that we gathered from Copernicus satellites, which are called Sentinels in this case, they grew enormously and significantly. And this led to an emergence of several cloud-based services, mostly residing in their own data silos. You can learn more about Copernicus series in the link down below. Well, the access and data discovery for Earth observation data is quite diverse, I must say. At UMESAT, we have UMESAT Data Access Services, which has data store APIs, and UMESAT Data Access Client called EMDAC. We have ECMWS Meteorological Archival and Retrieval System, MARS, and Production Data Store, ECPDS. Both of them has data APIs and clients. And we also have Climate Data Store, which is maintained by ECMWF, part of Copernicus project, which also has different set of APIs and clients. On the ESA side, we have Earth Observation Gateway and Copernicus Data Space Ecosystem. You can learn about them in the link down below. But why this is a problem? Well, trying to learn about different API systems, trying to learn how to authenticate them, trying to learn how you discover data or access data might be quite challenging. And most of the time, our meteorological institutions handling different data sets from multiple sources. So, for example, they are handling climate data from EUMETSAT, but they also need forecast data from ECMWF. They are also increasingly doing things with Python nowadays and using data processing frameworks like Dask. So having multiple data access methods might be challenging for them. They also face increasingly large data volumes that needs to be downloaded and moved across the systems because most of the time they already have some kind of an internal or external computing facilities that they need to download the data and process the data. Well, what about data federations? Well, I must say, good luck with that. Let me present you the idea and the challenges underneath it. So harmonized or federated data access it aims to provide Earth observation data access, discovery, and sometimes processing on different collections and products available under different providers. And I must say, this was a never-ending dream of ours. So in right-hand side, in the image, for example, you can see an example called EODAC, which has different data collections from different providers, and it offers APIs and clients to access them. And we have many others. We have Wikio HDA for Copernicus data. We have OpenEO, which is becoming slightly different, but really relevant. We have Destination Earth HDA, and we also have EODAC, as I mentioned. But you can see, you can probably quickly realize the problem with it. You are accessing a data set from an harmonized data access to another harmonized data access. So we put HDA in your HDA, so you can query while you can query. I must say, guys, this can raise some scalability issues, and I have some bad news as well. I believe personally we will never have a harmonized data access. So cloud to the rescue. Well, kinda. We had an idea. We thought if they cannot afford moving to data, we can let them compute near to the data. And this is how European Weather Cloud is born. Okay, I must say there are also similar clouds providing access to different collections such as Wikio, a European Union service for Copernicus data. But the idea is to simply move users near to data by providing computing resources. This is often called infrastructure as a service, allocated to their tenancy. You can think it as a community cloud where Earth observation uh, data processing community can come together and access to EO data. So European Weather Cloud, or EVC for short, is operated jointly by EUMETSAT and ECMWF, and it's based on OpenStack. So the idea is to have authorized users using similar interfaces and tools, creating virtual machines on either cloud that they have access already. So one example might be to have an ECMWF VM that digests downsamples and transfers only the necessary part of the data to a VM that runs in EUMETSAT, which does the satellite processing. I must say the data still stays in the silo in the respective cloud, and it is being accessed via the traditional formats, which I will come to that later. But this is already a huge way forward in how we do things with HDA, for example. But what about use case? What about the use cases that we need equal data from two or more parts of the cloud? One example might be to direct pixel by pixel comparison of a model and satellite observations. Well, this is still an open topic, but this was the best idea that we had so far. We also realized that there are some activities going on public clouds which can afford to move the data, and they also have a lot of compute. I must be honest with you folks, we cannot compete with the hyperscalers, especially on the computing part. And they already offer Earth observation data catalog to their users in cloud native formats. I will come to that later. Most of our users already are using or accustomed to at least one of the public cloud providers, and they are offering standardized APIs, for example, S3, to access and discover data, and they are becoming more popular and popular. And to be honest, they did move a lot of data. On the left-hand side, you can see Era 5 data in cloud-native formats, originally coming from ECMWF, from Microsoft Planetary Computer, and from the right-hand side, you can see Google Earth Engine data catalog, which has Sentinel collections in cloud-native formats. I must say that This is a huge step for public cloud users where they have access to data already and they can use the standardized APIs and the seamless integration that they have on the public cloud. But without going any further, let me stop by and talk about the data a little bit and cloud native data formats, of course. So what are they? Cloud native data formats, such as ZAR or cloud optimized GeoTIFF, they are structured in a special way to enable users efficiently retrieve data from cloud object storage, such as S3, to allow n-dimensional data access. But what does it mean? So in a traditional way, in order to access the data, you need to download the data in a legacy format. Let's say it's an FCDF file, although NetCDF is quite recent. So in order to get you started with the region of interest or region or the value that you are interested with or the variable that you're interested with, you need to download the collection and extract that kind of an information from the NetCDF file. You already require to download the data, which might take some time, and then extract the region of interest and start processing only then. This is a fundamental change that we are witnessing with the cloud native formats, which changes the traditional paradigm and allows users to access these chunks without storing and downloading or copying tailored data to start processing. It also enables users to rely on well-established data access and discovery APIs, such as S3, instead of trying to learn different array of software libraries, such as HDAs. So, multi-cloud to the rescue then. Well, one might argue that this might be the end for the community clouds. I think not really. I only think that we are at a critical point where we can transform the way we are working with Earth observation data. First of all, not all Earth observation data is available on public clouds due to several challenges on feasibility, the data is simply too big, or other practical limitations. But we can foster collaboration with public cloud providers to provide secure and platform agnostic ways to interacting with the data by implementing generic cloud native workflows. On the right-hand side, you can see an example where we published under the blog post in Dusk blog. You can access the link down below for details. But in an essence, we had in that prototype, which is called Data Proximate Compute prototype, two different clouds, one community cloud, European Weather Cloud, and one public cloud, Amazon Web Services. And European Weather Cloud has essentially two different clouds, EUMETSAT and ECMWF. We were using Amazon to host the client computer, in this case, a Juniper notebook. And we have attached the data that are available locally on ECMWF and EUMETSAT to ECMWF and EUMETSAT worker nodes to have local data access. Well, by embracing the simple distributed logic, we already stepped up a lot without even embracing the cloud native formats. So as you can see, we still mounted the data with NFS using traditional data formats. But on the right-hand side, which I will be explaining in detail, you can see a task screen with some numbers taken from the calculation. And if you look down below, the ECMWF workers showed in green, doing the bulk of reading and computation, while the red transfer tasks in the task screen joining with the data reads on EUMETSAT side. And this already reduced the calculation time from 14 minutes to 10 seconds with a feasible reduction on the measured network traffic. So we were copying less data and the calculation was taking lesser time. So this shows a community cloud in combination with one or two public cloud can work. But how we can mitigate the complexity of running a computation on multiple clouds? Well, this is how Terraform comes in and how Terraform bridges the multi-cloud gap for Earth observation community. Let me start by highlighting the feasibility of using Terraform in simplifying operations on multiple cloud, of course. So Terraform essentially providing us the much needed flexibility to consume Earth observation data or simply deploying infrastructure on multiple clouds. So by providing integration with almost every type of public/private cloud available with providers, Terraform makes our lives easier to deploy things without even need to develop additional tools on top. Of course, specialized workloads can be further offered by providing modules in form of Terraform modules, maybe tailored to the Earth observation community. But what I want to highlight is that this is not needed because we managed to provide additional services to our users in European Weather Cloud by simply integrating Terraform into our pipelines. We created for our users some blueprints in form of Terraform files for them to deploy hassle-free operations on their cloud. For example, on the right-hand side, you can see we are using a Rancher cluster template resource coming from Rancher provider in Terraform without even developing a module or anything additional on top to create a European Weather Cloud Kubernetes service for the end users. And we kept doing that. We created different library items for our users to deploy on European Weather Cloud to make them enable additional services on top. One example was, as I told, Kubernetes server, but the others are DAS cluster, the Umesat software stack, like data tailor and other stuff that I mentioned in my previous slides, and HT Condor batch processing environment. But I also would like to highlight its effect on simplified operations for engineers like myself. Because as soon as we start working with multi-cloud, we realize that multi-cloud also means multi-trouble. Multi-trouble when it comes to the operations, multi-trouble when it comes to have consistent configuration on multiple cloud infrastructure. And by simply integrating Terraform to our existing pipelines, we managed to build a machinery that can test, plan, and deploy infrastructure and infrastructure changes on the multi-cloud infrastructure that we have available. So as an example, you can see on the right-hand side that I was simply upgrading a Kubernetes version. And this commit triggered a change in my pipeline, in my CI/CD pipeline, which basically runs Terraform in the backend to do the planning and deployment after an approval, which is a huge increase on operations, reducing the overall overheat. We also managed to solve some everlasting issues, such as secret management in our pipelines with integrating Terraform with other available tools and other Hashicorp products such as Hashicorp Vault. Terraform provides an extensive list of integrations that you can integrate your pipeline with, and we were already using some tools like Ansible, GitLab CI/CD, external secrets operator to manage multiple things in our ecosystem. So probably you already know the secrets in CI/CD is a big topic, and I think you can all relate the challenges that you can face. But integrating Terraform with Vault and other tools that we have in the ecosystem enable us to solve the secret management, which was a big problem that I mentioned earlier, but also provided an opportunity for us to provide better service to our end users, such as managed Kubernetes, integration with Openstack in form of cloud computing resources, because that will require you to share the cloud credentials in a secure channel. You can see in the right-hand side down below. And Vault enabled us in close collaboration with Terraform to do just that. Well, after doing all that, we had an idea of replicable multi-cloud automation blueprints for Earth observation community. And a European Union Horizon project called Earth Observation for European Union, EU for EU for short, provided us an opportunity to cater the much needed Terraform scripts in form of modules targeted to the Earth observation community. You can see some screenshots on the right-hand side, and these modules, I must say, are still in progress, and we are trying to make them available for all Earth observation community to use in hopes of allowing further collaboration to build greater things. One example is the use case that we had in training at BITS conference, multi-cloud data proximate training. We already mentioned about the multi-cloud data proximate prototype that we had earlier, but Big Data in Space, or BIDS for short, conference allowed us to have a 2-hour demonstration and tutorial on multi-data proximate compute prototype, this time with cloud native data formats and multiple cloud backends. So Terraform with and with some extent Vault allowed us to build this training platform and build and manage this training platform required to showcase this use case. Well, to give you an idea, we hosted 30 registered and some unregistered users popped up during the training, carrying on computationally demanding tasks on 2 different clouds, EWC, European Weather Cloud, and VKO. Each user had 1 worker per cloud, hence 2 workers, and access to the cloud native data format. In this case, it was ZAR. This totaled around 200 vCPUs and 800 gigabytes of RAM. And you can see in the right-hand side a snippet from a Juniper notebook that we have. I will share the links in the next slide, where a user can easily create a cluster, a Dask cluster, spawning out in 2 different cloud infrastructure with the resources available to consume them. And I am not a scientist, and you can learn more about the science behind all that in the link that I'm showing here. But the whole calculation took around 10 minutes. And as I am told, this would be impossible to carry out with the traditional data access and processing methods. This already showed us how the leap can be if we use and utilize the correct tools to build such a platform. And I must tell you guys, it was powered by Terraform. So the machinery behind it to host this training use case was Terraform integrated with a couple of other things in form of modules and CI/CD pipelines. So we had Terraform and Ansible integrated together with some extent with Vault to build this training platform, scrap it, rebuild it again, and extend if needed. This kind of flexibility is impossible to achieve with traditional manual way of doing things. And Terraform provided the building tools that were necessary to build this kind of a training use case for Earth observation community. So where next? I think to infinity and beyond. I believe, especially after the training session at BITS, that multi-cloud architecture in combination with cloud native data formats is the future for Earth observation data processing. And Terraform can enable us to develop examples of such user-driven cloud-native workflows across multiple, either public or community clouds, cloud agnostic. And we are committed to improve our Terraform modules so that Earth observation community may create even more impressive things. Lastly, I would like to leave left some references and links to click. You can gather more information about the topics that I mentioned here. And if you have some questions, I am available at the chat. And thank you very much for your time and have a nice rest of the session. Goodbye.